You can look right now, see what you have.
Okay, so let's get going. Let's get going. We're going to wrap up energy, rotational energy, and then get into angular momentum. Now, I don't know why they say rotational energy and not rotational momentum. It's angular momentum, but tomato, same thing. Okay, so rotational energy, angular momentum. And so we already did see some of the equations for momentum. We put them in our table there. And so let me get it moved over. Why won't you move over? There we go. And so we've already seen some of those red equations there for momentum. And so that's coming, okay? Angular momentum. The hardest thing for you to grasp today, how can an object moving in a straight line have angular momentum? It's not rotating. It'll have a lever arm. So just keep, it's about your reference point. There's the answer. Okay, I'll say it over and over again, but that's the hardest thing to walk away on day one with angular momentum. How can you have angular momentum if you're going in a straight line? What? But lever arm, axis of rotation. And so let me just real quick see what we have. So we got page 2 started. I think I asked you to try and finish that out. Page 3, I don't know if y'all saw it, if you've needed to, but we actually have to make a correction on page 3. Ms. Earhart, get too excited. So where's the correction? We get slightly different answers here. And so here, let's grade what we previously did with this rod on a fixed axis at the end. It's a rod, not a circular object. I treated it, when I plugged in, I equals, oops, hold on. When I plugged in, I equals KMR squared. I used the right shape constant, but rods are not based on a radius, they're based on the full length. And so we need to rework this a little bit. It should be KML squared. So does R cancel? No. And so I'm just going to slide over to the side. Mass will still cancel. And so I'll slide over. We'll get GH equals 1/2 V squared plus 1/2 K L squared times V squared over R squared. So it was the L. Rods are based on the full length of the rod, not a radius, like a circular disc. So I was treating it like a circular disc. And so now we know some of these, right? We know some of these numbers? Yeah. And so the height change of your center of mass, still true. And so we can still say 10 times that 1 meter. We said we'll solve for that linear speed and then just plug it back in to get omega. By the way, we could have substituted out linear speed. We could have done omega from the beginning. I didn't want to make too many changes here. Plus 1/2 is part of the equation. K for a rod, you don't have to memorize it. When it's connected to one end is 1/3. So we did that previous. That part's the same. But here the length is not 1 meter. The length of the rod is 2 squared. And then V squared is what we're looking for. Now, what would the radius be? Because we picked the center of mass as the one doing torque or being our object that was falling, right? With the height change. And so for the R squared, we're still going to use 1, but notice it won't cancel out with L squared. Okay, so 2 squared is 4, 1/2 of 4, 2, right? So we'll get 2/3 V squared plus 1/2 V squared. Can we common denominator? 3/6 V squared plus 4/6 is 7/6, but wait, that's equal to 10, right? And so V squared, I'm trying to squeeze it in, multiply both sides by 6. Yeah. Oh, 12, hold on. 7? 60 over 7?
Oh, 7.
Because 3 plus 4, did I do that right?
No, I have it wrong.
Okay.
I have it wrong.
I mean, it is Monday, right? Obviously, yes. And so V, how much? You got to divide and take the square root. Yeah, because to solve for V. So previously, when we just used the radius incorrectly, we got 3.8. We're going to get something a little different. What do we get?
Okay. Oh, hold on. Oh, okay, okay. I think that should work.
You had it in parentheses. I think that should work. So I hear 2.9-ish. Did anyone else calculate? I just don't remember what we got last class. I know it's around the 3 ballpark. Okay, so I'm hearing 2.9, which is close, but different. And so that's our linear speed of the center of mass. Now, how do we find the angular speed? Well, just like we did previous, this part is the same, just different number. It'd be 2.9 divided by 1. We get an omega 2.9 radians per second. And then later they say, what is the speed, the linear speed of a point 1.5 meters away? And so it's the same setup. We just say, instead of 3.87, we'll use the 2.9. And so correcting here. And so 2.9 or 3 times 1.5 in the spirit of estimation, you get about 4.5-ish. And that would be not for the center of mass, not for the end, but at a point 1.5 meters from the hinge. You could do it for the end by using 2. Good deal? Okay. And you're not going to have, on an AP exam, on our exam, the inertia equation for a rod would be given, and it would say L, okay? I just quickly wrote MR squared, okay? My clock has slowed down. Okay, needs a new battery, so don't trust the clock there. Okay, and then page 4, yay, we worked. Pulleys with energy. Good with energy? It's okay. We'll still see a little bit of energy with angular momentum. They are cousins, right? Energy and momentum are related. Don't forget that. And so angular momentum, the equations that we wrote previous, we have a new variable for angular momentum. It's a capital L. Don't be confused with length.
Or variables that have other.
Yeah, so you got to look at context, okay? On the formula chart, which by the way, they're on this side if you want to grab one, but on the formula chart, capital L is labeled as angular momentum. It's equal to I, that inertia of the object, times omega, angular velocity. So instead of mass times linear velocity, we get that inertia, which has mass in it, but it also takes into account the shape, how the mass is distributed, times angular speed velocity.
Why are we reusing variables if we have like Greek letters?
I didn't make the rules.
Why stop it?
Okay. And then also consider that delta L, this is your impulse change in angular momentum, happens not because of a force times time. It happens because of how the force is distributed. You got that lever arm piece. And so it's torque times change in time. Tau times T.
And so BL is angular momentum?
Angular momentum.
Okay, or change.
Yeah, change in angular momentum. This is impulse for objects rotating. And so hopefully you remember that the big idea with momentum, bounces or changes in the direction, or also it changes in velocity or collisions. Okay, we're about to collide two rotating discs. And so collisions, okay, are a big thing to look for. And then don't forget, it's not on the formula chart. We had conservation of linear momentum. Well, we have conservation of angular momentum as well. And so during a collision, as long as there's no net, now I'm not just going to say force, angular momentum depends on torque. So if there's no net external torque on the system, then the net angular momentum before the collision equals the net momentum after the collision. Okay. And so, you know, previously we did a rod problem and we said, assume it's a frictionless rod, right? And so if there had been friction, there would have been a little impulse on the system. Friction is external always. Okay. So that's not on the formula chart. It's an application of a conservation law. So let's take a look at this page, page 5. It says two unequal discs are rotating in opposite directions about a horizontal axis. And so you can see that rod there. We'll assume that as they slide on the rod, there's no friction. And so just say no torque of friction.
They're not attached to the rod?
Somehow they are. The rod is preventing them from being in free fall. So just imagine if I had a little bitty hole and it was really, really smooth in the middle of this disc, and I put it in, and it's just going to spin on the rod, and then they're actually going to have linear motion as well and collide. Okay, why?
So we're moving it around and to the side.
Yes. And so, but the rod is frictionless. We just want to make sure that's clear. I don't think it's written. It says at a certain point after the collision, they begin spinning together. And so maybe initially they have opposite rotation, but eventually they're going to rotate together. Who's causing that opposite to stop and then they begin to rotate together? It's friction not with the rod, but friction with each other. Okay. And so there is friction during the collision. So let's review our collision rules. They stick together. There's going to be frictional losses due to the collision.
So it's inelastic?
What kind of inelastic does this remind you of? Completely or perfectly inelastic. That's actually the first question here. And so again, they stick together after. And the big physics to take into account, there is heat loss. So is mechanical energy conserved? Is kinetic energy conserved?
No.
No. Okay. And so KE not conserved. But your angular momentum still is in a collision, just like our linear momentum's conserved in these type of collisions. Angular momentum is conserved within our system. And you're like, but there's friction. Remember, it's the friction of the rod that I said was missing. If there was friction with the rod, that would affect the rotations before and after the collision. Okay, determine their final angular velocity and include direction. And so they do show us some clockwise, counterclockwise. Did they decide who was positive direction, negative direction?
No.
No, should it always be like the bigger number of whichever? How do we decide what's the positive and what's the negative?
The one that looks like it's gonna be the biggest. should be
Looks can be deceiving
Well,
sometimes.
that's fine.
So you have two options. You pick one and go with it. On the AP exam, that's honestly what I would do. Or you can kind of say, well, I'm going to use conservation of angular momentum, I omega. Who starts out with a bigger I omega? Just kind of like be proactive in a way. If you want to end with the positive, then you need to know what direction is the bigger direction. And so in your head, notice they give you I and omega for each. So who's going to have more angular momentum before the collision? The one on the right. And so not because it's bigger, but I omega, we've got 300 here, and it would just be what? Oh, we didn't talk about units, did we? This is going to be a messy one. Kilogram times meter squared over seconds. Yeah, I don't think that simplifies. And then the smaller disk visually would have an initial angular momentum of 200. Yeah. And so, go ahead. I mean, a good physics person does give units. True story in the multiple choice, maybe free response. They're going to test your knowledge of unit analysis. So an easy one is, what fundamental units make up a Newton? And your answer is kilogram times meter per second squared. And so they could ask, what is the equivalent unit of something like this? Free response, where you actually have to show work and write out. If there's a numerical response, I would always, I feel like I'd be a bad teacher to say, don't worry about units. But have I ever seen in the rubrics -1 point for a wrong unit? Not for AP1. AP-B used to do that. They also took off sig fig points, but now AP1, I don't see that written in the rubric, but you never know what this year's gonna bring. So I would do your best with units. Do your best, don't ignore them, appreciate them, right? Convert centimeter to meter, all that good stuff too. Okay, so with that, just a little proactive look into the future type, I'm gonna go with counterclockwise as being positive. Yeah, it's the standard, but I didn't do it because it was the standard. Forward wins, basically, right? And so this clockwise would be negative. Now this problem I don't think is really going to get into the linear pieces. We're trying to focus on the new stuff, but you know, I have a right, I have a left. So you want to make sure you're assigning direction there, being consistent. But just to find the final angular velocity, it's a collision. So we're going to go with that conservation of angular momentum. In the beginning, they each have, I'm just going to go 1 on the left, 2 on the right, and then they stick together. And so I can say L system final. And so if we hadn't done so already, you would want to do I1 omega initial plus I2 and its initial angular velocity. And then for the angular momentum of your system, it's not a total mass, it's a total inertia. And they have a shared final angular velocity. Okay, so that's what we're trying to solve for. Now, just to pretend we don't know the 200, 300, I'm going to plug them in so to be consistent here. And so the inertia of the first was 50. The initial angular velocity of this disk, we said it's going in the negative, and so I'm going to say -4 plus the 100 times a +3. Your system inertia would be that 50 plus 100. Up above, they gave us the inertia of the big disk. Yeah. And so -200 plus 300, we end up with 100 in the positive direction on the left, and then 150 times omega final, which is what? 2/3 or 0.67 should come out radians per second in the positive direction. Now, on the AP exam, if they say include direction and you're like, oh, positive, that's direction. By the way, your choice may be different than somebody else's choice, but you both answer positive, but you have direction. Positive and negative is assigned. So I would give them the actual direction. We said positive was counterclockwise. That you can agree with somebody who chose negative for counterclockwise. Okay. So hopefully it feels familiar, a little bit different, but it has that conservation, momentum approach, collision, familiarity. Determine how much thermal energy is produced as a result of the collision, AKA, what are we looking for? That heat loss, okay, due to the collision, not because of the rod. And so this is that heat loss. And for collisions, it's that change in kinetic energy, okay? And so change in kinetic energy is that final of the system minus initial of the system. And if we look at just before and just after, we're just going to focus on the rotational pieces. And so rotational, rotational. Now they have a shared final, but they each have their own initial, right? So maybe we come in and say minus, I guess let me make it another sentence. Final system, and we're going to use rotation for both, minus initial for 1 and minus initial for 2. And if you're thinking, shouldn't I have plussed them? Use parentheses, right? So if you want to plus them together, because they're both initial, make sure you use parentheses. I kind of distributed the minus to both. Tomato, tomato. Okay. So now our rotational kinetic energy, that's right, we're not done with it. It's that 1/2 I, and I'm going to use my subscripts, omega squared. And so it's the system inertia times the final angular velocity minus 1/2 of I1 and its initial angular velocity squared minus 1/2 I2 and its initial angular velocity squared. And I think we know all the answer or the numbers to plug in now. And so 1/2 I system was that 150. Final angular speed we had was that positive 0.67. By the way, positive, negative, does energy care what direction we're spinning?
No.
No, plus if I put in a negative, it's going to square away, right? So just a little reminder, momentum is a vector, angular momentum is a vector, but rotational kinetic energy is not.
Is it like scalar?
Scalar. And so I1, I'll do the 51, and it had the 4 radians per second. Don't forget to square. And then minus 1/2 of 100, this inertia of our bigger second object, and it was rotating 3.
That's a lot of that.
4 squared is 16. 1/2 of 16 is 8 times 50. Do we have the system kinetic? We're doing the energy, kinetic energy. Yeah. And so I get about 816. And you do get a negative. And if you're thinking, but Ms. Earhart, you said it was scalar. This is a change in kinetic energy. This is that heat loss, right? And so changes can be negative, but a kinetic energy at any given point is always a positive value. And it comes out in joules as well. Good old same unit for energy. Question? Yes. I mean, magnitude, yeah.
Would they take the points off?
They would probably rephrase the question a little differently. They'd probably say, determine the magnitude of the thermal energy. Yeah. But I'm just keeping with the negative so I can talk about it, right? Heat loss. Heat is leaving the system, energy is leaving the system due to the collision. Yeah, real quick I can. It's still in your content library. I don't know why this shifted down. Ugh, I think that made it worse. Okay, so on the next page, page 6, I'll come back later if needed. We're gonna, on page 6, we're gonna jump on a merry-go-round. Page 7, we'll jump off, okay? And so page 6, what is this merry-go-round? Well, first of all, I think, you know, early on at some point, I showed you a picture. Are there horses or are there not horses? It's a rotating disc, no horsies. This is going to be considered a top view since we see the full circle, right? And so the rotating platform that I've had in the room for a month now or whatever, just think of that. You're looking at it from the top. And so, and I'm not going to demonstrate this. I'm not going to put it in motion and try to jump off, okay? This is where we stay in physics land so nobody gets hurt. I would get hurt. And so we've got a 50-kilogram person over here on the side, our beautiful stick figure. They have a velocity of v, 3 meters per second. So that is a linear velocity, yes? And then they're going to run and jump on the merry-go-round. Now, in the beginning, they're going to jump at D. And so they're going to jump right here on the edge. The X where they jump in closer, that comes later. So just ignore that one for now. And they jump on this rotating disc, and it says it has a mass of 150 kilograms and a radius of 1.5, and then go on and give you the inertia of the MGR merry-go-round. 1/2 is your shape constant, and then mr squared. And yes, it's not a rod, so it's R, not L. Everybody good? If the child runs with a distance, and you can see that D labeled in the picture, that's equal to 1/2 the radius. And so again, not all these pictures are perfectly drawn to scale, but your axis of rotation is that big dot in the center, right? It's your center of mass for the rotating disc, and it's the axis of rotation. You come in with a lever arm, right? You've got a distance, and here's where I would say line of action. Yes, there will be a force exerted from the person onto the disc. You could call it line of force, but line of action. And you've got a perpendicular distance equal to the distance given. So a horizontal line of action gets a vertical lever arm. Everybody okay with that? So we're going to jump on the edge at this spot. What will be the final rotational speed, omega F, of the merry-go-round? And we'll assume, it doesn't say, but AP definitely gives the caveats. The student grips. The student is going to stay on the merry-go-round, okay? They're not going to slip off and leave, okay? So the child stays. In other words, what kind of collision is this? Completely inelastic, just like we saw before. And so we can use the same conservation of angular momentum that we did before. did they give us an initial angular velocity of the merry-go-round? No. So we'll assume that omega I of the merry-go-round is 0. So who has angular momentum before the collision? Who's rotating before the collision?
No.
No one. What? Then why, Miss Earhart, are you going to come in and say I person and their initial angular speed? What? We get to do a little derivation. Okay.
I don't.
And you'll see that the person, because they have a lever arm, has an angular momentum term. Okay. And so just bear with me, stay with me, stay with me. And so inertia they're not rotating, they're just going to run and jump. But because they have a lever arm, that's what we've been calling it, they have a distance about the axis of rotation. They have angular momentum terms. And basically at the end of the day, we know we're going to end spinning, right?
Yeah.
Okay, laws of physics, conservation of angular momentum, it has to come from somewhere. And you'll notice later that where the person jumps matters. And so the only way to get angular momentum after the collision is to have angular momentum before the collision. Conservation, right? And so even though the person's not rotating or spinning before the collision, let's do a little derivation. And so again, you don't have to memorize this, but a person, point mass, they're going to be on the outer radius, yes? So I'm going to go kmr squared, and this is all for the person. And then what can we plug in for omega? Remember how I said the student, the kid doesn't slip? So we have grip. It's going to be non-slip. And so remember, our non-slip velocity equation is V equals omega R. And so what can we do? We can plug in V over R for the angular speed of the person. Now, what do you notice happens? One set of R does cancel.
Isn't it like V over
R initial. There's only going to be one radius for the person. Right now, they're just sticking to the edge. Okay. But one set of R cancels. Oh, yeah. If you want to do, yeah. If you use omega initial, it's going to be V initial. There we go. And so now what's left? Well, K of a point mass, anytime you have a person, it's like a point mass, it's 1. And so we end up with mv r, and just again, to make sure we're aware what this radius is, it's not necessarily the radius that it rotates, it's the radius that the line of action happens with, the axis of rotation. And so I always write it as mv perpendicular lever arm, r perp. Y'all, that is the inertia of a person, of a point mass that's not rotating, but as long as it has a lever arm, it has a angular momentum quantity. Yeah.
How do you know, Ken? You just know?
Yeah, I'm telling you, it's 1.
Will they tell us on the exam?
Yes, always. No, let me say this. They won't always tell you 1, but if it's not 1, they'll tell you what it is. So if they don't give you a fraction, you can assume it's 1. Okay. I wish the equation was on the formula chart so we didn't have to have this discussion. I've been told that it's going to be on the formula chart in a couple years when they make some changes to the course. But as of right now, KMR squared, MR squared is not on the formula chart, but they would tell it to you. Similar to here, the disk, it's told 1/2 MR squared. It would be like that on the AP exam. They would just say it's inertia of the person is MR squared. So they'll just leave off the understood 1.
So it's always going to be there, but it's not. not gonna be.
A minimum sufficient amount of information will be there. Did they give you a fraction here? No, it's an understood one. Okay, so this M, it's the person's mass times their linear initial velocity. And so let me, oh, that should have said angular momentum for a point mass, by the way. L equals MVR. Now this one is not on the formula chart because it's a derived equation. But again, hopefully you use it so much you end up knowing it, right? And take a look right here. MV is what? What's MV? Linear momentum. MV is linear momentum times a lever arm gives you the angular momentum term. Okay. Okay. Or just derive it like I've done. And so there's your little lesson of how can an object that's not rotating or spinning or anything of the like, how can it have angular momentum? If it has a lever arm, it has angular momentum. Okay, and so we can take this MVR, I'm just going to kind of start fresh here. Our perp, we already said that the disk itself, there's an assumed it starts at rest, so we'll just say 0 for the merry-go-round. And then after the person sticks to the disk, they rotate together. And so it's the system inertia. And then that final angular speed that we're trying to solve for. So inertia of the I don't have a whole lot of room here, so I'm going to go up. We already kind of know how to get the inertia of the person, but we want to keep that R. And so let's go on and solve for inertia omega F. I'll be back over there. And so inertia of the person, we've got that understood 1 times 50. And the lever arm is half the distance, right? And so the distance is given to us. Actually, no, radius of the disk is given to us, 1.5. So what would our lever arm for the person running be? 0.75. Now, just so whoever's looking at this later, I'm going to go on and show 1.5 over 2. And don't forget to. Oh, wait. No. Scratch it. I almost did it again. This is the inertia after the collision. That's where we were. We already took care of before the collision. This is after that we need now. After the collision, the student has what radius of rotation? It's equal to the radius of the disk. So it's a full 1.5 squared. So imagine in your picture, after the collision, what circle is the student making about the axis of rotation? It's a full radius.
Wait, how?
He landed on the edge. Yeah, edge of the merry-go-round. That other picture of the person comes later. So it says the child runs, lands on the edge of the merry-go-round. So the initial lever arm for MVR perp is half of the radius. But now once after the collision, the child sticks, they're under non-slip, they're going to make a full radius rotation. Right here.
So they land not on the edge.
No, they do land on the edge.
Not the full radius.
The lever arm before is not the full radius because they run at a particular distance equal to half the radius. So the initial R and the final R are different for the child. Let it sit with you. We're going to also do some more with it, okay? Sometimes the more you see it, the more it clicks. So what's the inertia of the person after? What's 1.5 squared times 50? 112.5. And it would be that kilogram times meter squared. Now we can plug that number in to our conservation statement. We'll go back and hit the left in just a second. Okay, hold on. And so now the inertia of the merry-go-round, 1/2 is the shape constant given, mass is 250, and the radius of the merry-go-round is always the same here. You'd use the 1.5 squared. So this one should be bigger. What do we get? Did you do the half? Okay. Okay. And so that's the inertia of the disk because both are rotating after the collision. And so right side, check. Let's go back to the first part. Plug in some numbers. Mass of the person is going to be that 50. Initial velocity of the person, they said was 3. And we can say forward positive, right? There's not going to be, by the way, what would the positive rotating direction be? Clockwise. And so if we make to the right, when that student jumps on that spot, they're going to cause a clockwise. So that would have to be our positive direction. And so down in our equation, we go back, we got a 3. And the R perp, they're running at half that radius. And so it'd be the 1.5/2 here. And so what is that left side number? I get 112.5 equals 112.5 plus 281. Whoa, does that cancel? No, 1 is part of the addition. And so I get a final angular velocity of 0.3, 0.29, 0.3 radians per second. Good there? Okay. Let it sit for a little bit. What is the linear speed of the child while they're on the merry-go-round? Is it faster or slower than the initial speed? And so you could make a prediction. How would we find the linear speed after the collision? They're not moving in a straight line. Think tangent, right? So that tangent linear speed. And so when the kid is on the edge, they have a tangent velocity. Again, non-slip, use that V tangent, the linear piece equals the angular velocity times the distance. So all points on a merry-go-round, no matter where you sit, they're all going to have the same omega, but your linear tangent speeds are based on the radius. And so that 0.3 times, they're on the outer radius after the jump. And so we would get what tangent velocity? So that's where the student jumped on the edge. And so it's equal to the radius of the, oh, 1.5? Oh, I'm sorry. That was a total just bad memory. 1.5. And what do we get there? 4.5, we'll go with just my numbers here. I rounded, okay. And that would come out meters per second, okay? So just again, that non-slip application should be your friend. How much heat was produced? This is basically repeating what we did before, right? And so this is a collision. And so the heat produced is going to be that change in kinetic energy of your system. And so final And they're both rotating in the final. So this would be a rotational. But wait, no one's rotating beforehand, but energy is energy. It's scalar. It doesn't really care. So what kind of kinetic energy do we have before the collision? Linear, translational. Okay, and it's of the person or the child, whichever. And so final is going to be of our system. So I'm going to go variables before numbers. And so it would be equal to 1/2 I of the person plus I of the merry-go-round system times the final angular velocity squared minus 1/2 mass of the person times initial velocity linear squared. Now momentum, if you remember, let me give you a kind of big picture here. Momentum is a vector. So linear momentum is separate than angular momentum. They are conserved independently, yes? But energy is scalar. Energy doesn't care. So you can mix the rotational and translational, just like we did previous with pulley and ball going down the ramp, okay? And so to plug our numbers in, we got 1/2. The inertia of the person, we already found. It was that 112 number, I think. 0.5 or 2.5? 0.5. And then plus 281.25. So that's the system inertia. Final angular velocity after the collision was that my rounded 0.3 squared. Minus 1/2, the person's mass was 50, and they were going 3 meters per second. Don't forget to square. And so if it works out like before, we heat loss, it should come out as a negative change in kinetic. And so let's see. What now? No, it has inertia. If it has mass and a radius, it has inertia. It had no initial angular speed. It wasn't rotating in the beginning. And then times 0.5. So I get a 17.72 minus, and then 225. And so I get a negative 207 joules. Did y'all get that? Okay. I think it's okay. 207, 208. We did the same physics. Show your work. You'll be okay. Okay. Now let's make some changes. Put your thinking hat on here, because this is going to be, we're going to make several changes, but only one at a time. Okay. And so now part 4 says, for each of the following changes, indicate if the final rotational speed would increase, decrease, or stay the same. And so overall, up above where we used conservation of angular momentum, I'm going to bring that variable equation down. Now, if you want, we do know some numbers. You could do some numbers and get numerical answers to prove it to yourself, but the intent was to do it conceptually. And so that MP V initial R perp equals the inertia of the person plus the inertia of the merry-go-round, all times omega F. And so this is our working conceptual conservation of angular momentum equation that we're going to use. Everybody good? Okay, so what if the child's mass were to double? Well, let's go through the progression. What would happen to the initial angular momentum? It would double the initial angular momentum. And if angular momentum is conserved, that would mean you have a double final angular momentum. Well, it's kind of hidden in here, but isn't the mass of the person also in the inertia of the person? that MR squared. And so inertia of the person, I'm a semicolon, kind of a second train of thought, trying to save some space. The inertia of the person would double or be 2 times. But what about inertia of the system? Because really your final angular momentum is a system. Would your system double? No, you're going to add in the same original merry-go-round inertia. And so the inertia of the system would increase, but not double. And so what would happen to your final angular velocity? Well, this is the trick. Hold on. It would decrease. Yeah. We're so used to, oh, increase one, decrease the other. That's when it has the original equal angular momentum, but we still want to double. And so if you don't quite double with the inertia, your final angular momentum would have to increase a little, right? Something. It would have to increase for sure. And that one's, it feels a little different, but don't forget, you know, the double of the person happens on both sides, but it's not equivalent. System isn't equivalent. Okay, reset back to original mass of the child. Now, what if the merry-go-round's mass were to double? Well, go back over to the left-hand side. Initial angular momentum would. Initial angular momentum. It's only based on the person. And so if the person doesn't change on B, then angular momentum will be the same as it was before. And final angular momentum will be the same as it was before. And if you double the mass of the merry-go-round, well, what happens to the inertia of the merry-go-round? It doubles. What happens to the inertia of the system? It increases, but not double. And so again, your angular momentum is same as original. Now we have that inertia of the system going up. What has to happen to the angular velocity of the system? This is going to be the decrease. Okay. Mhm. Yeah, and B, because the angular momentum is the same, these two have an indirect or inverse relationship, right? But in the first one, your angular momentum needed to double in the first place, but the inertia alone couldn't double. It needed help. So it's not really a direct relationship, I don't want to say, but okay, now what if the child runs half as fast before jumping on? And so now initial velocity is half. What's that going to do to the angular momentum before the collision? It would be half, right? And so conservation of angular momentum, that means my final angular momentum would now be half as much. Is the inertia of either the person or merry-go-round different? No. And so a semicolon, separate thought, inertia of the system is the same. And so if I need the angular momentum to decrease by half, and inertia doesn't do it, who's going to get the decrease? Angular velocity will decrease. And specifically, here you can tell it would be half. Because we want that inertia, or because the inertia of the system is the same as the original. But you want half the angular momentum. Yeah. So if you go, go back up to the top, that VI is the only one that's affected when they run half as much. Again, here's what I would suggest. If you plug in some numbers, you can do half of 3. So do the numbers again and use that initial velocity 1.5. You can get a new answer. Okay, what color next? Now D and E, I'm going to draw some new pictures. So remember that up above, the person was inside at a different radius. That's coming now. Okay, so D and E, I'm going to draw new pictures. Just want to have to scroll back up. So D says the child landed not on the edge, but a distance X from the center. So maybe there was a snake on the edge of the merry-go-round and they just jumped over the snake, right? Me, I would totally run the other direction, but whatever. And so here's our kid, child, whoever. They are running, same initial velocity. The only difference is they're going to land right here. Okay. If you go to the original problem, the picture, that's still D. Okay, away. It's just now whenever they make a circle after the collision, how big is their circle? Smaller. Okay. And so using that same initial conservation of angular momentum equation, tell me about M of the person VI R perp. It's all going to be the same. R perp is the same. So this is all the same. So initial angular momentum is the same. Conservation. Final angular momentum is the same. But now what? If the child jumps closer to the axis of rotation, they make a smaller circle. So their MR squared is going to do what? It's going to decrease. The inertia of the merry-go-round would be the same, but overall the inertia of the system decreases, but I want the angular momentum to be the same as it once was. What does angular speed have to do? It's going to increase. Okay. All right. E, the child approached by the disc by running with a D equal to R. So this one is totally a new picture. And so here's our rotating disc. And now the person is higher up. And so the D equals R. And remember, this is the lever arm. It's that distance they're incoming. Okay. They still land on the edge. So when they rotate, now we're back to the full radius rotation, right? And so go back to the original M person, child, whoever, initial velocity. So the mass of the child, initial velocity hasn't been changed, but now what's true about our perp? It's bigger, it's doubled, yes. Okay, so it doubles. What's going to happen to our initial angular momentum? It's going to increase. Specifically, it would double, and it's conserved. So we're going to double there. And then final angular momentum is that system inertia times omega F. We're trying to figure out omega F. Now, compared to the original, where the child jumped on the edge, the child's still going to jump on the edge and make a full circle, right? And so inertia compared to the original is the same. And so what's going to happen to omega F? It's going to increase, specifically double. Appreciate the double when it happens, right? But if you increase, but not quite double, that's, you know, I've seen AP for multiple choice where those are answer choices, right? It doubles, it halves, it increases, but not double. It decreases, but not half, right? And so Appreciate it when it happens.
So is the only way to know whether or not the lower line is or like, is it just to look at the
Yes, because system inertia isn't a multiplication, it's an additive of the inertia of the person plus the inertia of the system, merry-go-round.
I'm just asking on like a more, not a practical, but like more theoretical. Like, so if we're gonna take a look at whether or not, like, if it called for the whole shebang in the question, it's like, it says, okay, based on this equation's angular velocity, but increase the wrong, and it's just whatever equation.
Yeah. And I mean, this one, we could have plugged in new numbers. I think that was all enough. Half as fast, you know, they run at full radius. You could go in and plug numbers in with the change and solve and see, does it increase and double? Does it increase and not double? You can see that too. Okay, how do we feel? Angular momentum? A little bit the same, a little bit different. Okay. The hardest part is just accepting that somebody moving in a straight line has angular momentum. It's where they run. And it's not on here. Where could the child run and not have angular momentum? Yeah, if they run right towards the center and they land, you know, maybe right here, then they don't have a lever arm. There is zero angular momentum, right, in the beginning. And so they would jump on. Would they even cause rotation? No. Okay. Now it might jiggle, but it wouldn't rotate, right? Real life, you'd have a jiggle, but it just wouldn't completely rotate.
So is it because he doesn't say R on that?
Yes, there's no R perp. And so I don't think we have time for this class, but page 7, maybe we're on a rotating platform and jump off safely. Again, I'm not going to demonstrate this in person. We'll keep it in physics land safety. And then page 8, what if we throw an object in a linear direction and it hits a rod, okay? And so I actually have a somewhat related video. I probably won't take class time to show it to you since we're running short on time, but I'll probably send it through Canvas if you want to watch it. It's firing a bullet at a block of wood a couple different ways, and one rotates, one does not. What changes do you expect? It's Veritasium. If you remember, I think I've showed you or sent them. I don't know. Veritasium, he does all those everyday type of examples, predictions. He gets people on the street to make a prediction. And so sometimes they're right, sometimes they're wrong, but he uses it to explain the physics. All right. So those definitely next class. And then hopefully we can get at least one NIMSY in. We only have one more class on Thursday, and then I'll see you on Monday. What's happening Monday? The rotation number 2 exam. It's our last rotation exclusive. And so, you know, do some practice. If you want to try jumping off the merry-go-round here. Well, we still have torque. There's still torque happening, right? You're still angularly accelerating. You're just not being asked right now, but you could have a combo question. And so it's just to finish it up. Okay. Don't forget torque. Don't forget the kinematics. We're just adding on with energy and momentum.